Then welcome to the 12th lecture in Introduction to Lattice Boltzmann. Today, after yesterday being last time being a little bit complicated, is not so difficult because we're just talking about some algorithmic aspects, and in the exercise later we'll continue implementing the multi-scale grid refinement lattice Boltzmann code that we did not finish last week. So if you're interested in this will be at the end of the video, unless I'm screwing it up. Okay, let's see. It's not so straightforward, actually. So efficient implementation, I've written down a few sentences here on what we are going to consider. So here we want to have efficient methods. Okay, efficiency has several aspects. Yeah, efficiency means that, for example, our method uses the is accurate, because an accurate method is also efficient, or an inaccurate method is also inefficient. Yeah, because it usually requires a lot of resources. So by inaccurate, yeah, we do not mean that there are mistakes in it. Inaccurate, we mean that it is low order and therefore requires high resolution to get to something that can be done with a lower resolution with another method. So the cumulant methods that we promote here as being better than, for example, the BGK, has lots more floating point operations, even that we saw this even in 2D, but in 3D it becomes even worse. So that we have to consider, then we have efficiency-wise, we have the problem between we have to read and write data, and we have to do operations on data. And in this respect, the cumulant method is actually good, because it does not require more data than the BGK. Yeah. So, I mean, it requires 27 velocities and not 19, for example, but it's like BGK otherwise. And on modern computer, we say that floating point operations, you could say, come almost for free, which is a good thing for the cumulant method, but the memory access, this is the expensive part. So what we usually try to do is somehow, when we move memory around and move data around, we try to overlap this with some calculations. Lattice Boltzmann, if you read the literature on efficiency, computer science, lattice Boltzmann, so to speak, they often claim that lattice Boltzmann is always band limited. Yeah, so we had in the lecture last semester, we discussed about compute limited and band limited. We can go back to this. Lattice Boltzmann requires a lot of data and usually not so many calculations. This means it's often considered to be band limited, and when it's band limited, then you can increase the number of calculations without making it much more expensive. So the observation is that this is not necessarily true for the cumulant method. The cumulant method can be compute limited. Interestingly, if you do everything you can do to optimize these computations, then you can make it just so band limited. And that's a good thing, because this would mean that it's pretty well balanced. Yeah, so you don't necessarily want to have a compute or limited or bandwidth limited code, because I mean from an efficiency point of view from your computer, yeah. So if you have a strongly compute limited or strongly bandwidth limited code, then the other resource of your computer is not well used. So basically you bought the wrong computer for your purpose. So the best is always when you have a balance between bandwidth limited and compute limited. So, and then there is something that is often not considered to be a part of efficiency, but I consider this differently, as we will see in this lecture. Namely, there's a problem that you observe if you do more operations. It's not only that this takes more time, but having more operations also means that you have an accumulation of more round of errors. At least in lattice Boltzmann, yeah. So there is so in numerics you always have to distinguish between direct methods, so explicit methods, and iterative methods, yeah. And direct or explicit methods have the problem of accumulation of round-off errors, and iterative methods don't have this problem, or not to the same extent, yeah. Okay, so this is where we also want to start, namely with round-off errors. So understand round-off errors. So in here we'll do this in 2 steps. Yeah, we first consider data loss in storage, and later we'll discuss data loss in computation. Okay, so say we have the populations Fij, they are superpositions of the moments. MABC. So we can, in principle, write the populations Fijk as a sum over A, B, and C over some, if it's raw moments, then we could have here constant tensor alpha ij k a b c. So that's a tensor with, you enter the index and then comes out a number, and this we multiply with MABC. So this is basically, that would be a matrix. So you can consider this as a matrix operation, yeah? But I don't write it as a matrix operation. So basically what I want to say is that these physical quantities, like the velocity, so what we learned, yeah, like the velocity, the pressure, and the shear stress, and all of this is somehow stored in the moment, yeah. But it is stored, so we turn everything, even if we do the calculations in terms of moments or cumulants, we turn all of this into a distribution, because distribution is the thing that we have to move around, yeah. In streaming, we just stream this distribution with its populations. This means so the content of these various moments are all get into a superposition onto this F. So the problem with this, as we'll discuss in a minute, is that these physical quantities, which are in the moments, they are of different asymptotical order. Yeah. By the way, there's a problem that always makes solving the Navier-Stokes equation difficult, because we have things of different order in it. So now let's just look how do we deal with this kind of thing. So we have the populations get stored in terms of floating point numbers. And floating point numbers are, of course, not perfect. So, an example, they are not floating point numbers are not all the same, but let's stick to the usual ones. We have a standard IEEE 754, and this defines different floating point numbers just as a demonstration. And because we've written our code in the 32-bit floats, so this used to be standard precision. Now, since we are in the age of artificial intelligence, yeah, these there are many more smaller data types, like 16-bit, 8-bit, 4-bit. Actually, 4-bit floating point is really amazing. It has 1 bit, often for an exponent. So the question is, why does this? So okay, let's see whether you listen to what I was just saying. Why does deep learning work? Why do deep learning people love these 8-bit floating point number, 4-bit floating point numbers?
To compute much faster.
Yeah. Okay. I also love to be faster. So, but why is this not good for me? And why is it good for them? Yeah. So they like accuracy?
They will produce a lower accurate model plus maybe some correction model.
Yeah. So for one thing is they can spread this out over a network. Yeah, that's one thing. But just for what I was saying. So of course, deep learning is an iterative process.
Oh yeah.
Yeah. So they do not accumulate round of errors in the learning phase. Yeah. Whereas we in lattice Boltzmann dealing with an explicit algorithm, and so we have the problem of accumulation of round of errors. So so far we always benefited from the development of graphics cards, and so because they are not only good for deep learning, but they are also good for lattice Boltzmann. But lattice Boltzmann has difficulties with very small data type. Actually, I've seen that there is 16-bit lattice Boltzmann also out there. Papers have been written. Sorry. Okay, let's look at this number. So how is this built? I kind of assume that you know, but I'll tell you anyway. So there is 1 bit for the sign. Then there is 1, 2, 3, 4, 5, 6, 7, 8. 8-bit for the exponent. And then there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So there's 23 bits for the fraction or mantissa, yeah? So I guess you all learned this somewhere else. So this is where we place our numbers in. So now the problem that we are facing here with these floating point numbers is that all moments, because they are all in the same number, yeah? So all moments share the same exponent, the same space in the fraction because they are stored with the same exponent. And here the problem, as I just said, is that, which does not fit here very well, is that moments vary in their asymptotic scales. Okay, next page. So let's look at this in our favorite scaling, the diffusive scaling. So diffusive scaling again means delta t is proportional to delta x square is proportional to epsilon square. Right, so this is how we define this. And then we have different physical quantities at different orders. So to epsilon to the order 0, what we have is the actual density of the fluid. So density, this is rho to 0 order. So epsilon to 0 order is a constant, yeah? So this is their background density, yeah? So it's for air, what do we have for air? 1 kilogram per roughly 1.24 kilogram per cubic meter. And for water, it would be 1,000 kilogram per cubic meter. So that would be kind of this density, yeah. And we assume that this doesn't change. So epsilon to the first order, there we have velocity, because we have epsilon u first order, yeah, because I remind you, u, so our physical u, okay, we write the physical u, I believe we have written the physical u with an asterisk, I don't remember quite, but this is the, oh, okay, no, I didn't, okay, no, okay, get rid of this asterisk. The u, the solution of the, whether it has a unit or not, doesn't matter, yeah? The u as the solution of the, that we get, the numerical solution, is asymptotically the epsilon times u to first order. This is the solution of the Navier-Stokes equation, yeah? Because we saw this pops out in the asymptotic analysis, yeah? And then on top of this, so the next term is missing because it's a symmetric method. So then it's epsilon to the order 3. And so on, these here are error terms. So the error terms also exist. Yeah, we don't want to have them, but they are still here. But there's also other things. For example, the pressure. Pressure is not the only thing, but so pressure, with pressure, I mean the differential pressure, not the absolute pressure, yeah? So this is epsilon square comes to rho to second order, so the variation in density, and this times theta. So this gives us the pressure in the Navier-Stokes equation. So, and we already see they are different order. So what does this mean cartoonishly? And this, I mean, not my stupid faces here, but let's have a cartoon on what that means. So epsilon is a small parameter. So this means that epsilon to the order 0 is much larger than epsilon to the order 1, which is much larger than epsilon to the order 2, and so on. So since this is the case, the variables are actually scale separated because they have different asymptotic scales. But still they are stored in the same fraction. So now comes my cartoon. Say, here's my fraction, and I just cartoonishly write this as a vector here. And now there's big endian and little endian. I will now say this here is my most significant bit. And this here is my least significant bit. So now everything is stored in all our moments are stored in the same fraction, in the same vector here. So for example, if we look at rho to the 0 order, so this is a constant and it is larger than is the largest thing that we have. So what we'll observe is that this is using the entire fraction to be stored. So then we have as the next thing, say I'm always doing this wrong. So let me put it here. Yeah, as I said, this is a cartoon. Say here we have epsilon u1. So this is where we store our velocity. Yeah, so this is because our velocity is smaller, it's asymptotically smaller than the density, it starts later. Yeah, meaning that the velocity uses this amount of the fraction. Now, the pressure comes an order lower, and the shear stress also comes an order lower. So roughly speaking, I have to take the same distance that I had between these two. Yeah, so very roughly. So I'll put this roughly here and say, for example, here we have epsilon squared theta rho, second order, and we have dx u to first order, so the shear stress. Yeah, they are all located here, and the amount of space they occupy is this here. And then there are also things that we call ghost moments, and they start from the third order onwards, and say, okay, let me just say this is the ghost of third order. Okay, and this ghost of third order, this has this amount of space in the fraction, which means that here, so these are the effective the effective number of bits available for each quantity. Okay, for whatever reason, I've written down a stupid example. Maybe I do this quickly because it's simple, yeah. But anyway, let's look at it anyway. So say rho 0, we say the density is 1, and U is 0.01 delta x by delta t. Yeah, so that would be a typical velocity boundary condition that we set. So what would this imply? This would imply that we have a pressure variation that's proportional to U square in size. So it does not need to have, the proportionality constant can also be 100 and so on. Yeah, but anyway, it would be of that size. So it means that we have here 0.0001 as a typical size. So okay, you tell me whether what I'm explaining here is too simple so that I can maybe compared to other things that we discussed, this is pretty straightforward. Yeah, rho 0 is the largest and defines the exponent. So the exponent is chosen according to what rho 0 is. So the exponent of the floating point number, which means that rho 0 is stored in all 23 bits. So the actual definition of this is there is an implicit bit, so that is actually you can use 24. Yeah, because the exponent, so you always shift to the first bit being 1. Yeah, so there is one implicit bit. So you can actually write this thing like this. So it would be 1 dot. Now getting a little bit okay, I hope I have written down these things correctly. So this is the numbers. So 3, 4, 5, 6, 7. Okay, so this in binary. Yeah, this is the number that we would have in binary if rho is 1. So then our velocity, which is rho, which is u divided by rho 0, yeah, this is 0.01, and this can now be rewritten as in binary as 0, 0, 0, 0, 0, 0, 0, 1. Okay, I'm not making you write this if you don't like, it's just for demonstration. Yeah, so this is the number that we have here in binary, and what we see here is that for this number, which is a usual number, yeah, we have lost 7 bits. 7 out of 23. Yeah, so I want to point out how significant this thing is. This is why we do it in practice, even though it's pretty simple. Yeah. So now saying this here is of second order, so it would be of the size 0.0.0 0, 0 in decimal, and that would translate into 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, and 1, 0 in binary. Okay, so obviously, I mean, we lost 14 bits lost. And now this goes so on. If I mean, to the third order, we have, of course, 21 bit lost, 21 out of 23. Yeah. Which is kind of significant. 21 is a significant amount of 23. Okay. And yeah. So in this example, of course, this is an example, and you can have, I mean, you can have smaller velocities, obviously, yeah. In this case, each order in epsilon loses 7 bits. As I said, just example, more in the fraction. So, of course, as this is an example, this depends on what we have been starting with. So what is your velocity on the start? So this is the magnitude of the epsilon 1 variables, which of course is velocity to the first order. New page. So what's, I mean, so we scale them physically, and this has to do with the time step, of course, yeah? So the smaller we make the time step, the smaller is the numerical value of the epsilon 1 term, yeah? So the smaller the time step, the smaller u to first order becomes. And then the even smaller are the higher moments. So we can also make, I'm not sure this makes exactly sense. I also tried this out and didn't see it properly, but let's just think this through. So the maximal ratio of the smallest to largest variables. So assuming that the smallest variable is presented by 1 bit, which you could say doesn't make any sense, yeah, to represent a variable by being here or not here, yeah. So, but this would be 2 to the power of 23, obviously, which is not that terribly large. It's just 8 million. Yeah. So you see, the largest thing in this 8,388,608, which means that the smallest thing can only be 8 million times smaller than the largest thing that you have in the same variable here. So, and it's pretty easy to get out of this range. As an example, saying that epsilon to the first order is now 10 to the power of minus 4. Yeah. So you want to have very accurate results, so you use small time step. Then epsilon squared theta rho to second order would be 10 by the power of minus 8, which is, of course, much smaller than 2 over 1 over 2 by the power of 23. So, which means, and you can try this out, maybe it's not directly at this number because there are factors in front of it, but which means that if you do what you are told here and what mathematicians will tell you, so you should think asymptotically. You make your time step smaller and smaller and smaller. What you end up with is that you do not have any detectable pressure anymore. Yeah, so you can completely lose the detection of pressure, and that anything happens with pressure just due to this. So let me point this out. Flows, and you actually see this. Yeah, so if you try to plot the pressure, there is nothing. There's just numerical noise. Flows with velocities smaller or equal 10 by the power of minus 4 delta x by delta t have no detectable variation in pressure. And the same thing is of course, is true for the shear rate, because it's of the same order. Yeah, and then you run into all sorts of problems. Okay, so now I told you the problem. What is the solution? So there are a couple of ways to deal with this, and we call these methods altogether, we call them conditioning. Yeah, so maybe, I mean, I made it clear that I'm not a mathematician, so mathematicians may have a slightly more accurate definition for this, but let me define what we in this lecture consider to be conditioning. Yeah, so the conditioning is the reformulation of a problem with the aim to reduce rounds of errors. So you can condition the entire thing, and you can condition simple single computations, and we'll go through a few, basically 2 examples of what we are doing. So, as is often the case in the world, the simplest measures are also the most effective. And the simplest measure that you could think of is to have rho 0, which is a constant, so it does not contain any information because it's a constant, so there is no need to store it. So let's remove this. So what we're doing is we define something else. We have a delta Fijk, which is Fijk minus Wij, and this Wij, this is the lattice weights which are very present in the usual BGK lattice Boltzmann methods. Here we don't use them so often. So they are constant weights, and if we sum over them, over Ijk, so they will give us rho 0. Yeah, this is just this constant. So now what we are doing is nice haircut. Now we store this delta Fijk. So let's just have our cartoon again, the fraction. Say this here is my fraction, and this here is my most significant bit. So the other one would be then the least significant bit. And now, because there is no row, the thing we are starting off is with U1. Yeah, so U1 now has the entire space. And say we have here this epsilon squared theta rho second order. This will come using this space, and the ghosts of third order will also have a lot of space. So this is again the effective available bits, and they have of course increased now. Yeah, so now there is, I mean, this is pretty trivial, yeah, but there is one thing that I've still seen people doing wrong, because it is trivial in principle, but can get challenging in practice, because you have to remember one important thing. Whenever you put something in form of this f, it will be reduced. It will be put into this. It will cover the entire fraction with the 0 in front, with the constant in front. Yeah. And therefore it is essential, and this can get pretty difficult actually if you don't watch out. It is essential, and really essential is essential. So I write this in red. It is essential that the well-conditioned, so this now we call the well-conditioned state is maintained throughout all computations. So, see, when there is somewhere in between something that you have to calculate, where you have to return to your original f, so it's tempting just to add 1. Yeah? Once you have done this, everything that you saved so far is gone. This means while you're doing, it is not sufficient to store them like this and send them off in the streaming, but everything in between. You always have to keep this state. Yeah? And this can actually be becoming difficult. So here there's one again. If you don't want to have this problem, go to the machine learning guys. So this is what everybody does currently anyway, because machine learning is iterative. So they don't have accumulation of round of errors. But we live in this other world where we have explicit algorithms and we have this problem. So, and here, I should not price machine learning that much. They also have problems. Yeah, so the accuracy of the simulation. So this is one then you should keep in mind that this is limited by, now in caps, by the operation with the least accuracy. Okay, so this, okay, technically I must correct me, because technically this does not have anything to do with accumulation of round of errors. Yeah, this simply means that if you are in any place in between, you do a calculation with an unfortunate format, so everything that you have saved so far is being cut out. Yeah. So for that reason, now we come to our point number 2, which is the data loss in computation. So I didn't want to talk too much nonsense today, but maybe that one still. The first implementation, or the first 2 implementations of the cumulant methods, did not show any improvement because of their bad conditioning. Yeah, so we had here a PhD student implementing this full scale, more or less the same way we implemented it in 2D 2 weeks ago. Yeah, so this is not a clever way to implement this. And when we did this in 3D, there was actually so much noise that there was no use for it actually. So since then we have studied ways of reducing round of errors a lot, and we have not used them that much in the implementation that we show here. But if you really, if you want to build an airplane, yeah, so you absolutely need to know how many times you have to turn your screw, right? So if you build a cupboard for your living room, you can do IKEA stuff. But if you do precision engineering, yeah, then everything has to be accurate. And this is unfortunately also true if you want to write a proper simulation code. I mean, this is now not limited to lattice Boltzmann, but in lattice Boltzmann we have this particular problem that we have an explicit algorithm, which we want to have because explicit algorithms are very, very fast, but they are very, very prone to round-off errors. So you really have to watch out how you implement stuff. Okay. Okay, but I'm reducing myself here to ignoring this here. So for clarity, we use the unconditioned. The other thing is you have to do everything you have to do together, yeah, at the same time. Yeah. So just to make it better understandable, we use the populations, the usual populations Fij, k below, because combining this with what we said before is even more complicated. Yeah, it's not. I mean, yeah. Before I said there's a simple what we do. I mean, it's relatively simple, but still you have to watch out. Okay, what do we naively do in lattice Boltzmann? We compute moments. For example, we compute the velocity. Let's look at the velocity. So u is 1 over the zero moment. Yeah, we divide by the zero moment, and then we sum over ij and k from -1 to 1 over I Fij k. And of course, you can implement this as a triple loop if you will, right? Yeah. So then if you implement this as a triple loop, or you actually write it straight out, what you have is you have a summation. You have a summation over 27 numbers, because, I mean, you have 27 populations, of which in that particular case 9 would be 0. Because 9 times I is 0, so they would disappear. So I mean, if you write it as a loop, you have the additional inefficiency that 1/4 of this is doing nothing, yeah, because you just add 0. By the way, adding 0 is a good operation because it goes without round-off error. Yeah. So what is the error usually of this? So summing n numbers has round-off error of the order of n times delta. Actually, it's n minus 1 times delta because you have one operation less. Yeah, but that not so important. Yeah. So what is delta? Delta is the value of the least significant Of course, the problem is you can, okay, so we assume, and this is a very hard assumption here, that they all have the same least significant bit. Yeah, so it's becoming more problematic if they have different, and they usually have. Yeah. Okay. So we can do this. I remember. there's one question I like to ask the students usually. Maybe I can see whether the online guys are awake. What is making more round of errors, summation or multiplication? Any opinions online? Yeah, please. Just either say something or write it in the chat.
Multiplication.
Multiplication. Why does everybody say multiplication has higher? Because it's a more complicated operation, yeah? Actually, multiplication does not make, so in multiplication, the exponents are combined and the fraction, so every, the two fractions get aligned in a multiplication, yeah? So the round off error that you have is only the least significant bit of the result. Yeah? So in summation, you have the least significant bit of what is going in as an error. Yeah, so summation is more prone to a round off errors than multiplication. Okay, this is why we focus here on the errors in summation and not in multiplication. So there are more accurate ways of summing. You may have heard about the Kahan algorithm for summation. No, so this is an algorithm that is using bookkeeping to minimize summation errors, and this can also be done in a recursive way, so that is actually an optimal algorithm. The problem with this algorithm is that you do something relatively simple, like summing up things, with a relatively complicated algorithm. So this takes much more time. Yeah. So because we are greedy, we want to have low round-off errors, but we don't want to pay anything for it, right? This is like in cumulant, we want to have more accuracy than BGK, but we don't want to pay anything. So we use the same discretization. So what we can do that has the same price, computational price tag as a normal summation is the so there are different ways. I often say this is the pyramid algorithm, but this is only my own wording. It's called the cascade or pairwise summation. So if you're not familiar, you will just learn this in a minute. And in lattice Boltzmann, in addition to this pairwise summation, we do some pre-ordering. Actually, pre-ordering is a part of the summation, but pre-ordering. So you should actually pre-order your numbers according to their size. Now, I just said that we don't want to pay anything for it, and if you do reordering before you do the summation, that is, of course, costly. So now what we do is we do a static reordering, which is not perfect, but which is better than doing nothing, okay? So, because what we observe is that we actually have different least significant bits for the different directions. So least significant bit value depends on the lattice direction, because it's usually proportional to these lattice weights. So yeah, due to different weights. The weights are the same weights that we are using for weighted orthogonalization. If we make an MRT with weighted orthogonalization, yeah, which is, again, as I told you, not the typical way of doing this. So Paul Deller has done something like this, but the classical ones are not. Wait. Before you write, I made a mistake. Sorry. So D3, let's look at D3Q27. So here we have the weights for the ones in the fully diagonal direction 111, yeah. So this has a weight of 1/216. This plane diagonal, you want to say this is, you see, this is 4 times, so it has two bits less, yeah, already. More, sorry, it's the inverse, it has more, yeah. W10 has 2/27, which is again 4, factor 4. And then again, we have a factor 4, 8/27 for the resting population, for the weight of the resting population. So you see, the most significant bit of the resting population is larger than for the one in this cardinal direction, which is larger than the one in this diagonal direction in the plane, which is larger than the one in the diagonal, in the fully diagonal, yeah? So, and now we use this for our pre-ordering. So with pre-ordering, I'm not meaning that you pre-order your lunch. I mean, it's pre-order putting in the right order, yeah? Separate, so we use separate classes by direction. So I'll put 3 classes. So we have so for computing the weight. Okay, let's compute. We should probably write this. Compute M100. So 9 of them were disappeared. Yeah. So we'll not talk about them. But say we have the class of populations that come with W111. We have a class with W110, and we have a class with W100, and we have no class with 000 because this is not part of this moment. So now we build an algorithm, a summation algorithm in steps. And I will do here step number 1, and I will now indicate what we are summing up. We are summing here Fij k minus f minus I minus j and minus k, yeah. And now we distinguish them, so none of them should be 0, because when they are 0, they belong to the next class. So here we have the class F1. Oh, now, yes, I see your face, and I hope you're writing not on paper. If you write on paper, then so it's F, sorry. So because it's velocity in x direction, they all have 1 here, right? So sorry for mistyping. Fi, so my 1 and an I looks very similar. And I unfortunately still have the habit to read from my script. So F1 jk minus F minus 1 minus j minus k, yeah? So now you see, we can vary j and k. How many times? So we'll what we do in step number 1 is we combine 2 of them and we combine another 2 of them. So there's four of these, right? So four variations of these, and we always combine 2. So we okay. So these x's symbolize the permutations. Yeah. So, and on the other side we have this class. So f10 k minus f minus 10 k minus k, and also we have here in the same class f1j 0 minus f1 minus j0. And of these we have 2 permutations, and here also 2 permutations. And in the last class we have f100 minus f minus 100, out of which there is only 1 permutation. So in this first step, we add these things together, right? And then in a second step, we add these permutations together. So this happens in step number 2. And then after this, we have a step number 3 where we add again these permutations. Yeah. So, and I mean, you may have seen this already in the code, because this is how we actually calculated it in the code. Yeah. So we put these brackets. Yeah, where we always had the one and the one that's going in the opposite direction. Yeah, and we tick these brackets. Yeah, this is what we are doing here. This is why we put these brackets. Now we have a step number 4. In this we add this, and now we have a step number 5 where we add these here together. And after step number 5, we have our moment M100. So now what you see, the number of summons is 18. So which means that a naive summation would have an error of 17, because I mean it's n minus 1 delta. Yeah. So if we do pairwise summation, we actually add up. We gain one round of error only in one of these layers. Yeah. So, and now we don't have 7. We don't do this 17 times, but we do it only 5 times, because we only go through 5 steps. And this uses this in pairwise summation steps is basically the binary logarithm, which I just write as log. So the ceiling of the binary logarithm of 18, which is 5. So the error that we accumulate here in pairwise summation, of course this gets better the larger your sum is O delta the log of n, which is usually smaller or equal than this delta n minus 1, or you can forget about this 1, yeah? So this is why you should always use these pairwise summations. We don't do this all the time in the when we code here, because we don't have a lot of, because writing is more complicated, but maybe this is didactical stupid of me, and I should always do this. So in the real code, it's always done like this. Okay, so far this. Now coming to, I thought we are quick today. Okay, something else. So second example, how we get, first of all, faster. So sometimes things that are, sometimes you get all of it. Sometimes you get something that has low round-off errors and is faster. Yeah, because you reduce the number of computations. And one such thing is the chimera transform. Okay, what is the chimera transform about? When we want to compute cumulants, I told you that the easiest way of computing cumulants is from first taking central moments and then turning them into cumulants. Yeah. So what you still require is to compute these central moments. So we have this transformation from populations to central moments. And this turns out to be very expensive. So you have to do it one way, and then you also have to do it backwards again. So let's remind us what is the naive way of doing this. Naive transformation. So we call these central moments, we write them with K. KABC is equal to the sum over I, J, K from -1 to 1, Fij, K, then with I minus U to A, J minus V to B, and K minus W to C. So what we see here, if we take all of this together to be one number, which is not correct, because obviously you have to compute these exponents, right? Or these polynomials, then you'll have 27 populations that you have to add up for 27 moments. Yeah? So you have 27 times 27. This is what you have to compute. And this is the most expensive part of the algorithm, or one of the most expensive. I mean, okay, as far as we ignore crit refinement is the most expensive part of the algorithm, yeah. But this is a standard part, and it's expensive. So crit refinement, or crit interfacing or boundary condition, we only need in specific places. This is something that you have to do everywhere all the time. Yeah. So how to get this small? And this is I always tell the story that when we wanted to publish this, the reviewer for the paper told us that this is so trivial, we should not, I mean, this does not belong in the paper because everything else about cumulants is so complicated, just forget this. Okay, why I'm telling you this? Because I always want to prize myself, maybe that's the reason, but the thing is that simple things that look very, very trivial make a very big difference, because before we had this chimera transform, the cumulant method didn't work really. It had too large round of errors and it was simply too expensive. Now the chimera transform changes everything in a drastic way, and you will, and it is so simple that the reviewer said, so this is so trivial, don't even bother publishing this. Yeah. So what are we talking about? So a chimera is something that is part one thing and part another thing. Yeah. So, and we call these things, so parts, we call these things that are part distribution and part moment. Yeah. And maybe it's a little bit misleading, but you always need to give things a name, and it's better they sound cool. Yeah. So what do I mean? I don't want to compute this thing here directly. So what I do is I compute a different quantity, which I now also call k. Yeah. So because it's already part a moment, but I keep the indices for the populations I and j intact. Yeah. And then I write a line because I want to do some indication. And here I write the moment in C. So what we do, we integrate in the C direction, but not in the I and J direction. Yeah. So which means we get here the sum over K is minus 1 to 1 Fij so over everything. So this, of course, small k, this is capital K. Sorry for not having that many letters. So, and then we multiply this by K minus W and C. So what we are doing here is 27 times 3. And again, this is still less than what we did above because we only have this polynomial in one direction here, yeah, not the entire thing that we had here. So, but if we just count how many sums we are doing, we do 27 times 3. So now we continue this by integrating the y direction. So, and this becomes now b, so k, I, b, c, by taking in and integrating now over j from minus 1 to 1, not f, but what we had before, k, I, j, and c, and here we have j minus v by the power of b. And this is again 27 times 3. And then lastly, we get to k, a, b, c by integrating over the x direction. By I is equal to 1 to 1, and this is k, what we just computed, I, b, c, I minus u to the power of a, where we have 27 times 3 again. Okay, now you could agree that this is a completely trivial rewriting of what we had before. Yeah. However, already here you see that this is 27 times 9 operation. So this very simple rewriting of how you compute the sum reduces the number of summations already by a factor of 3. And here we have not yet taken into account that the inner part of what we sum over has become smaller because these polynomials have become smaller. Yeah. So, and this was so complicated for me that I actually let so that I didn't try to model it, I let Mathematica count the operations for me. So that I can now tell you, okay, maybe just writing this down, since each term in the chimera transformation has fewer operations than in the naive form, the savings are actually larger. So let's compare. You have naive and you have chimera. So when I implemented a small program in Mathematica that would count the operations, and I counted additions in the naive transform 1482. So this is one-way transformation, yeah? So in one-way transformation, at every lattice point, in every time step, you have to do 1482 additions just to get to the central moments that then you still have to transform into cumulants before you can actually do this is only the transformation, yeah? So what do we have in the chimera? We have 270, yeah? So multiplications, very similar, 1452. Yeah, it's almost the same number as the summations. Yeah. So in chimera 162. So all of this together means that we have 1/5 the number of operations required. And you know what? This is not the good thing about it. There is something extremely more important, which is not so obvious. Yeah, and okay, well, we don't have this time to go through this in detail. I made one experiment which is potentially not representative, yeah, but this is in line with what we observe in the actual simulations, yeah. So because we have this many operations that we have to do, and if we do an unordered sum, yeah, so then we have this problem. Now you see there's 1,400 summations. Yeah, of course you can divide by 27 because they go to the different moments anyway. But so you have a lot of accumulation of round-off errors, and if you do this split up, it actually acts like a pairwise summation. And if you also in the internal, you can also a little bit optimize the internal parts of this. And now what you see is that a single, in 3 dimensions, of course, a single naive transformation can lose 10 significant bits more. Okay, so how did I measure this? I have an input, I transform this, I transform it back, and I measure how many bits are different, yeah? So the chimera transform is not perfect, but the thing that I have observed by non-representative samples is that using the naive transformation can lose me 10 significant bits more than when I use the chimera transform, and the chimera transform again is not perfect. Now this explains, for me at least, why it was initially difficult to implement the cumulant method, yeah, because if in any transformation, in every time step that you do, you lose 10 significant bits. I mean, again, they are at the end of, so when you do it the next time, so they will roughly stay within this more or less the 10. It's not that every time step you lose 10 significant bits, that would be terrible. But this, if you use single precision, this is already half of your precision that you lost just doing the transformation without having actually done anything numerical. So now officially we have only 2 minutes left, but there is one more thing that I want to add here, and that has to do with efficiency in implementation, and this is the esoteric twist. Now we are done with numerics and we are just going to algorithm now. Yeah? Esoteric twist has nothing to do with computations, it's just how you implement your streaming. Because now we're talking about the collision, yeah, so far, and now we come to the streaming. Now the streaming is very simple, so how can you make simple things even simpler? That's the question. In the code that we built here, we've already said that streaming and collision should be combined so that you read things only once. Because otherwise, if you do this in 2 steps, you have to read populations, do something, write them back, and then you have to read them again and write them back again. So that is what you want to avoid. So you have read once, write once. Now, what is the problem with this? Is that we see we need 2 representations of our data. Yeah, so we have somewhere where we read from, and we have somewhere where we write to, and this can be done in 2 different ways. There is the push scheme, which is writing to the neighbor. This is the one that we have been implemented in our code, yeah? So basically this looks like this. So I have fi of x. So I just use one index for clarity here. Now plus the vector in which the population looks. This is ei delta x t plus delta t. So we write, so, and this gets the outcome of the collision of fi x and t. Or you could say the post-collision part. Yeah? Why did I write it like this? Okay, I don't know. So now we can now say this here is matrix A and this here is matrix B. And what we do after we did this operation is we exchange A for B and B for A, and then we do a swap. Yeah, this is what we call a swap. So, and similar, this can be implemented in a pull scheme where we read from the neighbor okay, I'm too dyslexic to write this properly. Neighbor, so what we do here is we have fi. So now here is only x t plus delta t, so the next time step. What we do is when we read the population before the collision, we take them from the neighbor. So we go here now in the negative direction, yeah, delta x and delta t. So we read them from the neighbor. So this is not what we implemented. And then again, we do the swap between A and B. Okay, if not the A, we read from B, and maybe you can decide to define this other way. You read from B and read from A and write to B, maybe. So now the push scheme is usually a little bit simpler to visualize. This is why we also implemented it this way. The pull scheme is often faster. Than push. Yeah, the reason for this is that reading is less so like non-aligned, so non-cache aligned. Yeah, non-cache aligned, reads are less expensive than non-cache aligned writes. So this is why you should actually rather use pull rather than push. So now I was teaching you stupid stuff. But you can improve on this and see whether this actually makes a difference. So both of these things are called A-B patterns. Because they have two matrices and they call them A and B. So both A-B patterns. So we do a read from B, write to A, then reverse order. Okay, now there is an alternative to this, and this is called in-place streaming. So there are several in-place streaming algorithms, but we will discuss only one here, yeah, because we are already run over everything here. So what we mean in principle with in-place streaming, lattice Boltzmann is in one regard different from most the other numerical methods, in that it has an operation that starts with q real numbers and as an input and has an output of q real numbers, right? So this is only possible, if you think about this, this is only possible if they are all the same. Yeah. So once you read something, you don't need it anymore. No of your neighbors needs them anymore. Yeah. So then there is no need to store what you've just read. So you need only one representation. So this is different from finite differences, for example. Yeah, there you always need the values at your neighbor. So you have a larger. So you read. So if you do very, very simple forward in time finite difference, yeah. So you want to write one at each point. You want to output one result that depends on two neighbors. Yeah. So you have this discrepancy. So you have to hold your neighbor's data. Here you don't need to do this. So here question: is it possible to read and write from A to A? Yeah, and of course it is. Now, using one array. Okay, so this was pre-major. Okay, now I show you how one possibility how this is done. Yeah, and I'll make it here simple in 1D. So we have D1, Q3, right? So, and now we place our data in 3 arrays. So say we put an array A, data B, and data C. And you'll understand why I have these strange names here. And say these here are the data. And each data cell is corresponding with a certain lattice node. Yeah? So okay, I should stop doing this. So in here we have fi minus. So we distinguish between even time step and odd time step. This is, by the way, also in A and B pattern, we also distinguish between even and odd time step, which we can do by flipping pointers in C. Yeah, but so we have an even time step, and we talk about the read. So f minus 1 is now read at data A at the position n plus 1. So say n plus 1 is the one here. So this is n plus 1. Yeah. Then we read f0. F0 is the data B, and we read this at the position n, and the position n is of course this here. Yeah, and also the next one will have f1 dc, so data c of n. So then we do our collision, and then what we have to do is to write this back. Now we are only allowed to write to the data that we previously read. Yeah, but if we do this, we would not stream if we just write them back, so they would always stay in the same position. So, but what we have to do is we have to put one of the populations, because it's moving, one to the left and the other one to the right, which we can do by flipping DA and DC. Yeah. So what we do in the right, we now write dA n plus 1. Here we write f1 star, so this is what we previously got from DC. DB, n, here we store again the one that is not moving. Yeah, so this will just stay where it is. And DC, n, will have f minus 1 star. Now we have obtained what we want to do. We have moved the f1, we have moved this one to the right, and the f minus 1 to the left. Yeah? So, and then we have to do this the other way in the odd time step. So odd time step, here we have the read. Now we have a different interpretation of than we had before. So we read f minus 1, now not from as we had before. Before we read it from DA, but we put this in C. So we put it in DC, n plus 1. Yeah, you see still the same, there's the same pattern. Yeah, we read f minus 1 to the right. Yeah, and we put f0 again from dB and n dBn and f1 is equal dA and n. So what we did is we reinterpret where we store our data. Yeah. So, and if we write this again, we put it in the previous state. So DC n plus 1. Now comes f1. The bn is f0 and the an is f minus 1. So, and then we are back in the original state. Yeah. And by so doing, we have moved everything while we were reading everything only once and writing it only once. So this can be extended in 2 and 3 dimensions. Here I just draw a picture how you can imagine this in 2 dimensions. So you do the read like this. So if this is your original node, yeah, so you put here the ones that are moving in these directions, the ones that move in this direction is at this neighbor, and these are at these neighbors. Yeah, so they all have to move according to their direction. Now you have put them into the right. So when you write them back, you always get the one that move in the opposite, directly in the opposite direction, and write them back like this. So, the reason why this is done specifically like this is that, you see, we need access to our neighbors only in one direction. And this has the advantage that if we are not in a matrix code, as in our example, what we have what is this called, a sparse matrix representation, yeah, a list code, then we only need to know the neighbors to one side, which is an advantage because we only need to be linked to one side. So in addition of having only one matrix, we also can save about the number of pointers that we need to get to our neighbors. Yeah, so access Now I know how I misspelled neighbor up there. But so there's this American joke that Germans cannot say neighbor. Neighbor. So access to neighbors only required in positive direction. So this means we have low bookkeeping costs for sparse matrices. No bookkeeping costs for indirect addressing, which is sparse matrix. Oops. And here what there is also often used. So in principle, in 2 dimensions, it would be sufficient to have one pointer in the very minimum, but this is not done in practice. Because in one direction you could line them up in the array, and in the other direction you have to have a pointer, and then because you have to go to the corner, what you do, so usually we have 2 pointers, one in X and one in Y, but what you do is you go to your X neighbor, and then from there on you go to your Y neighbor, yeah, by using pointer chasing. So this is how you can access, you can stream to 26 neighbors by just having 3 pointers. Yeah. Okay, and this, so important for this method is that it is that it's thread safe, so all of this can be done in arbitrary order of execution. And therefore it can also all done in parallel. And this is what we usually want to do with GPU computation, right? So that's okay. I do this later. So that was the lecture, and now I had made the promise, the unfortunate promise, that we are going to do grid refinement. So before we do this, are there any questions that I should answer about on the lecture? Because okay, so somebody just seems to agree. Then yes, then we'll. Do you have any questions to the lecture? So it's not that complicated, but a few tricks we still have, yeah. So, okay, let me see whether I'm in the right code. So I honestly have to admit I did practice a little bit, because I also stopped last time, not only because it was late, but because I ran a little bit out of my concept. Yeah. So let's very briefly recap what we did, and maybe you can stick the videos later together. So the thing is, I was told by one of you that I should not call this grid refinement, even though this is how we usually call this, but multi-scale simulation. Yeah, because what we want to do is we want to run the same simulation where we have one simulation where we have part high resolution and part low resolution. Okay, so for this we have here made our struct interpolation function. So we use these polynomials to do the interpolation. So these are the interpolation coefficients. Then we have set up here a child. Yeah. So this is the first thing I want to change in this code. So I practice a little bit. So this is why I have a little bit of paper in front of me. Yeah, because I have to admit this thing is not so terribly straightforward if you try to do it, completely ad hoc. Yeah, and the problem is how you find your how you synchronize your coordinates. This is usually a little bit tricky. So okay, what we should do here, let me get a little bit rearranged. What we should do here is to okay, I will have this as demo LBM 2025. So this should return us, this, because we have to call it later from. So let's return this and say this is return child. Okay, so this is the first change that we do today. Then what else did we do? So here we compute the interpolation coefficients. So for specific given coordinates, we compute these coefficients here. And here you see it, we have these pairwise sums. So we use pairwise sums here already. So right. And here we use the we use the second order moments or the second order cumulants to get the gradients in velocity in order to enhance our polynomial to do the to get a quadratic interpolation, even though we have only four points. Okay, and this is done for the x and the y velocity, and then the density we just use for the density we just use bilinear interpolation. And as you see, we've taken these out of Mathematica, and here we now did not use the proper summation. So if you implement this seriously, you should use pairwise summation here. But I'm not going to do this because it's just getting too complicated today. So I'm not doing my own teaching today, because otherwise we don't get to anything. So constructor, destructor. And then this is the last thing that I think we've implemented here is set non-equilibrium. So at a position x, y, we set rho 0, u and ux, uy, and so also the non-equilibrium cumulants, second order cumulants. So we compute the moments from these cumulants, and then we set them here into the populations in this position. And this is the pre-collision populations. Then later we have to collide them. Okay. Yes, and we can do this because we do a push. So that would become more. So this would become more complicated if we had a pull here. So in reality, now you have to remember what we should do in reality. We should first of all subtract rho 0 everywhere. So then we should use these correct summations. Then we should use the chimera transform when we compute the cumulants, and then we should use esoteric twists. Yeah, all of this together, and all of this we are not doing today, okay? So that equilibrium was an older function. And here are some collision operators that we are left with, and here we have MRT, and cumulants. This is the one that we are using, and swap here. So, and now we were here. This is where we came to. Yeah. So here we wanted to compute the recursive. We wanted to do this recursively. So we're doing this for t time steps, or steps, time steps. We count over t. Yeah. And now what we do is we run one course time step. And now if this has a child, yeah, if it doesn't have a child, we are done here. Yeah. If it has a child, we also run two time steps here with the child, because the time step is here shorter. And now comes the thing where we stopped, where we have this coupling algorithm. Yeah. So, and there I was already starting to be a little bit starting being confusing, and I noticed this is not going to work, so I had to stop here. Maybe. Okay, let's look. We do what we want to do is we want to loop over so we want to generate on the coarse mesh, yeah, in the surrounding of this patch, we want to generate the interpolated coarse lattice nodes that we interpolate from the fine lattice nodes. Now there is an overlap, and we have to identify this. We have to identify the width of this overlap here. And I wrote here some numbers. They are not correct. I have to admit, I spent on the weekend and on Friday several hours to figure this out. So it's not. So I think, in my opinion, this is the complicated part. Maybe I mean, you can either just believe me, or I'll make a picture. So grid interfacing. So I now take the liberty. So lecture is here over. I put this in the same page. Yeah. So say this here is our fine grid. And now this is very much implementation dependent, because you can do everything in different ways. Now, because we are using this pull algorithm, yeah, we decided that we have our array one grid layer larger. Yeah. So that the outer meaning that what I have here sorry. So these outer here, they are not in use. So we just forget them, but they are part of the data. Now this is our fine grid, and say we have our coarse grid. We have our coarse grid like this. So in this example, we do not cut out the coarse grid under the fine grid. In reality, you would always do this. Yeah? But for the purpose of the demonstration here, we'll not do this. So how large do we need to go? I think we'll need one more. So our problem is we have here plenty, we need plenty of overlap. I misaligned this, right? Yes, I misaligned this. So we need plenty of overlap. What am I doing? So this is the reason why this takes so long, because you have to identify stuff. So the thing is, we are going to use this here as a cell to compute these 4 fine grids. Yeah? And this here as a so here we have, so they are actually continuous here. So now I notice I didn't have enough of them. So the next ones are going to be here, 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 and here. So again, we have a cell here, and now we are roughly coming to the point where we want to be. So see, this here is the first. Maybe I'm continuing this here. So this here, so this will go on like this, and here we can finally have our first interpolation. So these are interpolation cells. Yeah. So now the question is, how do we get from the fine to our coarse? Yeah. So you see, this here is index. Sorry. This here is index 0, index 1, index 2, index 3, index 4. Yeah. So now let's go to our code. So this is, and we identify, this is important, we identify the cell always by its, lower corner here. Yeah. So we have to go 4 in. Okay. So now, did I write this? No, I didn't. We have to go 4 in. Now that I'm not messing it up, I'm looking in my cheat sheet from now on, right? Because the other way, okay, I used equal. That's maybe so. From the other side, yeah, we have to go in one further, and in my cheat sheet I have used smaller equal, so I used this here too. Yeah, so this comes from the other side, and then we count this up by 2. Yeah, because we go up. Yeah, so we go from here to here, so not to the next one, because here's nothing. Yeah. Okay, then we get the cell. Okay, now very important. Now if this here is a 4, then the other one, the other direction is of course also 4. Yeah. We have to be very careful. If we make one mistake, nothing will work. Okay. So then, right. So we compute we get this coefficients, and then we compute the moments in the center. Yeah, so this is why we only need the first parameter a0 and b0, and then for c x y we take the derivative. Yeah, and since we take the derivative of a by y, so we end up with ay with the thing that does not have any x to it, right? And the same thing here. So this is what we already did last time. And we do this on one side of this box, and then we have to do it on the other side of the box. Okay, now, yeah, this is not, so before we do it on the other side of the box, we have to write it to where we want to have it. And there I made another mistake. Let me see. So this is not xi minus 5, but it's actually the origin, the starting point, divided by 2. Let us see that this is, so the origin is this here. Now we start with x equal to 4, yeah, and we divide by 2, so we get up 1, 2 here, right? So this is starting point. X starts from 4, so we end up here. Okay. So we got this here, and we are. So now this, and here we also have to, not at the starting point, but we also have to go 2 up. Yeah, also go 2 up. Okay. Is this understandable? I mean, okay, so I have to admit, keeping track of this is the difficult part. Yeah, so let's hope I'm doing it correctly, because I fear that also you won't keep completely track of all of this all the time. Now, so this was one line. Yeah, one line of x. Now comes the other line of x. So this is this here has, of course, to correspond with this up here, and here we have -5, where I said I believe this is correct, which is of course nonsense. This also must be 6, yeah, because it's a 6 up there. So let me see my cheat sheet. Child get interpolation coefficient, xi, child get rows -6, okay? So then we repeat all of this, and then we have to write this in the right position. Here again, this is not -5, but xe2, and from here, again, it's not -5, but it's -6. Yeah, and we always have to divide by 2 because our steps are smaller. Okay, and so we have written it, and so we are done with what we have prepared. So now we have the 2 lines in x. Yeah. Now what we have to do now next is to repeat all of this in y. So I'll take the liberty of copying this. This was wrong. What did I do? So I take the liberty of copying this and just pasting it here. Yeah. So this is where I copied it to. So we have to do it for y. So Okay, for simplicity reasons, I'm going to do the corners twice. Yeah, in principle, you could take one of them shorter. Yeah, but I don't want to mess up things, so I'll try to keep it simple. Yeah, so let's do it Y, and then instead of cols, it will be rows. And here Y, Y. So now, hopefully, we don't make any mistakes. All we have to do is to exchange these indices, right? And also, of course, these. So here, now this is very dangerous. Here you can easily make a mistake, yeah, so please, that's your job now. You always look that X is in front and Y is later. Otherwise, we'll mess up. So, and here also possibility of mistake. Possibility of mistake is that we forget about rows and columns. And we do this and we get rid of the comma. Okay, so now there's one more, right? Oh. So Y, cols, and X, okay? Satisfied? So in principle, let me see. Should save this and see whether we made any. No, what am I doing? Let's just see whether it compiles. It's a good sign that it takes long. Yeah. So it compiles. So now what have we done? We have coupled so we have copied the define to the course. Yeah. So meaning we now got this node here out of the find grid. Well, this will only work when on the other side we get these nodes here from the course grid. Yeah. So now comes the annoying part of all of this. So, right. Let's go here. So now again, we do this in 2 loops. Yeah. And this is for, again, we do this in, okay, now there's one thing that I want to do before. You see, we had this scale up, yeah, because we had to account for the change in our coordinate system, that delta x changes, and here we have to scale this up, and the scale up was doubling. You know, the scale up is doubling, yeah, this size. So we have to have a scale down that is using scale down. So this is basically 0.5. So that's we have to do first. Then we go. So the coordinates where we start from. So this here is coordinate 0, this here is coordinate 1, and this is where we want to be. Yeah. So I'll start with xe is equal to 1. Xe is equal to 1 is equal to 1. Then xi is smaller equal. Okay, I know this is stupid, but this is the way I have it on my cheat sheet, and because we want to get done today, I'll not deviate too much from this. So, of course, we get, yes, so how many columns we have, and from these we subtract 2, yeah, because we go 1. I mean, this I've not drawn this, but this is, I mean, this is the highest number. So, and then we get to, on the other, when we flip it, we want to get to this point, yeah? So we go to this minus 2, and then we, again, we are in the high resolution grid, so we do xe plus 2. Now we have again to take the interpolation coefficient cell that we get from get interpolation coefficient. So now we have to find the point. Now the point is now, you see, this is a grid that is inside another grid. So here this is not position 0, but this is the origin of where we put the origin, yeah? And we have introduced a variable for this that we've already used up there. This was origin child x. So in the x position, we always have to use x, and in the y, we always have to use y. And then we have to have xi. And now there is, we want to start from the actual position, yeah, from here. So in order to do this, we have to put this to 0, so it's xi minus 1. And since our steps, since we go 1 lattice node each, see, we go from, the next cell is here, so we go only 1 lattice node each. This is why we have to divide this by 2, and this will start at the right position, yeah, because this is still 0, and so it will be origin x. This will be origin x, and right, and then origin y. So, zack. Now we have the interpolation cell. So now it's a bit more, I mean, you can simplify a lot of these things a lot, but this is not what I want to show. So we'll do it very boom, yeah, kind of way. So what we need is coordinates xx and yy. So coordinates within our cell. So I want to repeat, I mean, I want to repeat everything that I write so that I'm not messing it up. So what I'm going to do is I put my local coordinates here every time, yeah? And I start with this corner here. So what is the coordinate of this? This is 1/4 in each, the coordinate system is in the middle. Yeah? So this means this here is 1/2. Minus 1/2. So this point here is at minus 1/4, yeah? So I'll have to put for this point here minus 0.25 and yy equals to minus 0.25. And then we want to compute, okay, well, maybe I'm taking these guys up here because this is what we want to compute, yeah? But you'll see that this will get more complicated now because they are no longer in the center. So I have to have this entire polynomial here. Yeah, so I'm now going to write out this polynomial as, do I have to? Yes, I think I have to. Unfortunately, I have to write out the polynomial as, okay, I'm copying this. Cell A. So what do we have? X times XX plus Y times YY plus XX times XX times XX plus YY times YY times YY plus XY times XX times YY. Okay? Can we believe this? So if we can believe this, I will now copy this, put it here, and try to replace all of them by B. And you watch out that I don't make a mistake, because that will get an ugly result. So now I have them always B. Okay, now this is scale down. All of them become scale down. And here we need to be careful now. So what we had here is, so you see, here we didn't have A0 and B0, but this was the derivative of this polynomial, of the A polynomial in Y, and the one of the B polynomial in B. But there are, of course, more parts. Now, bear with me, because that's okay, it's not terribly complicated, but you can make mistakes. So say, how's this going on? So we take AYY, yeah, times YY, because we take, we have taken one derivative of Y here. So there's already a mistake here, because when I take the derivative in Y, we get this twice, right? So that's possibility of mistake. Lots of possibilities of mistake here. We can use Mathematica to generate this. This would be, maybe that would be better. But so, and then there is XY, and this comes only with X. And then there are no more, yeah, because there are everything that does not has an Y in it, yeah, has been eliminated by this derivative. Now, the same thing goes for this B part. Maybe I'm going to put this here, I don't know. So the B part, so what you could say is that BXX comes in XX, yeah, also with 2. and then we have bxy times yy. Okay? So, now what's about that guy? So this guy here is only the x derivative. So there is this with x again, but then I have to have it twice, 2 times this times xx plus xy times yy. Okay? Hopefully still reasonable. And then we have this here 2 times that y times yy plus xy times xx. So, okay, and now see, okay, so how's this done? This is, yes, so this is x times xx plus y times yy plus xy times xx times yy. Okay, so this should be the way this should work, right? Now we have calculated this. Now we have to put this back into now the child. So we have the child, and in the child we have to set non-EQ, and we do this in these coordinates here. So we start C. So we want to be, so we go in over the x direction, and here we want to be in place number 1 because place number 0 is outside our domain. Okay. That means this is xi and 1 and rho 0 and ux and uy and cxy and cxx and cyy. And of course I have to do this properly. Okay, now we set the first point. So now next thing is we go over the other 3, and for them we have to do all of this again. So one thing, unfortunately, we cannot. Okay, we are going to recycle. We are going to recycle these. So I'll not redefine them. And we now take a different node. So say I go one further in x, then this will be here x plus 1, right? Maybe it's not, what I'm currently doing is not good design, because when I make a mistake, so I copy this now for x times, and when I make a mistake, I have to repair it x times, yeah? But still, okay, so this is currently the faster way of doing it. Okay, I told you something about what we call it, the only change one, yeah. See, this is, if you have a good design, though, you don't need to bother about this. So next time why does it look like this? So we are changing x to -1, and this will take this here to 1. So now we have done it 4 times. We have done it 4 times. So I'm going on with my cheat sheet. So, so this was the one line, so we do it the other line, yeah? The opposite. So we have to compute a new cell. So basically, no, I'm not, okay, I'm just copying. No, I'm not copying at all. I'm doing this. So this is, I don't know whether this is upper or lower, but anyway, it's the other line, yeah? So we get cell is equal to get interpolation coefficients. So the origin x plus x I minus 1 and 1/2, and then I have to go to the other that's okay. So on the other end we have origin child y plus, so we need to have the number of rows. This is from the child, yeah, from the child. So child get rows, and there we have to subtract 3 and have to divide by 2. So this is what I figured out after a few wrong iterations. So from here on, okay, I'm starting with this, even though this is stupid. So I don't want to write all of them again. So now we have to locate it correctly. So xi is, I believe, should still be correct. So we'll actually have to go to this position here. Let me rows. Yes. So this is child get rows -3, where we have to set this. Okay, now when we do the copying of this, okay, this was stupid. So let's change this one, and then we have to get rid of we already have to get rid of this here, right? So don't, I mean, that's your exercise, you have to tell me, yeah? Okay, I mean, I noticed this is not so straightforward. Then probably need some help. See, this is something that you should never do. Stopping right in the. So, I moved x one further on, so that would imply that we go on one here. Yeah. Okay. So then we have done two of them. So let's do the third one. The third one is going 1 on in y. This means when we subtract 2 here, we are subtracting 3 here, we are subtracting 2. And now we have, let me see, minus plus. So that would be that one. So is this the right, wait, let me see whether we mixed anything. Okay, it seems like we still get a compilation. So, yeah, sorry, that's not good style, but what should I do? Okay, so we did x direction and we do it in y direction. Wait, where are we? Here. Yes, so we do it in y direction. And again, so in principle, so I'm going to do the corners twice so that I don't need to think, okay? So then this is rows y. So, okay, we get, now we have to get this here correctly. So we'll get here an x, here an y, and here an y, okay? Now we go on one. Okay, now since what I'm going to do is exchanging x with y, it makes me require less thinking if I also change it here, right? Because when I do it here, I can simply copy, yeah, copy this here. You understand what I mean? Requires for me less thinking, and thinking currently is dangerous. So then so that would be the same. So x so here I exchange these and So the other one. So what we have to change is x. So here must be cos, this must be y, and this must be y, okay? So far so good. So, and then in this we have to so here this is cos and this is y. So here we have the one little mistake and nothing will work. That's, oh my God, what a pressure. Because I spent a lot of debugging for my cheat sheet. So here, and cos. Okay, that one. Okay, now we are at the end of this. So let's save and let's compile. Okay, in principle, now it could be done, right? Now we have done everything. Okay, so now you see I prepared here something. Okay, since we are also longer in time, I made a new Jupyter notebook. By the way, I'm not completely sure that we've done everything. I think, no, we have not exported it. Yeah, so that's, I think we are even missing several things that we should have exported. Yeah, for example, getting the what is it? Do I have this get child? Yes, okay. Yes, we have to export it. So, but that's put dot dev run. So we called it run recursive, right? Run recursive and demo LBM 2025. Okay, we need to export one more thing, namely we need to the get child. Yeah, we have to this. I mean, we can also export other things, but the other things are not. The other things are required internally. Yeah, so we can export them, but we don't need to. Set child. Set. So let me see whether. Okay, while we are compiling, yeah. So in order to prepare this, I prepared a new file here, and so because this is the other thing that made me a little bit nervous. We only it's not sufficient that we have the code that runs it, but we also have to display it. Yeah, and for this, I was not aware how to actually do this. So, and because I'm not what is this, Python programmer. So here, I did what everybody does nowadays. I just asked ChatGPT to write me a program that would overlay these two pictures. By the way, this took several iterations until it worked. So it's not, apparently that's not, I mean, it's possible, but it doesn't seem to be so straightforward. And you can impress me if you get a working lattice Boltzmann with grid refinement. Lattice Boltzmann is easy, but lattice Boltzmann with grid refinement just from using artificial intelligence, yeah, because I think there's not enough example code out there to actually do this. But maybe we just about to change it here, yeah? So, okay, I just explain. So we read our demo file, then we set columns and rows and some omega, maybe I'll not have that high omega. And then we load this with columns and rows. And then here I will set some boundary conditions, yeah. And we've done it like this, that when we set equilibrium around it, so it will set the velocity, and I set the velocity to here this, okay, I'll start with a higher value. I set the velocity, and then I set this in the y direction, and then I put bounce back around here, so this will give us a velocity boundary condition everywhere around, which you will see looks ugly, but this is not my point today. We just continue with what we have. We put it everywhere around. So then I put at position X 20 and 10, and with a width and a height of 18 times whatever way I did this, I set my child as LBM2, LBM set child at the starting position with the size of the thing. And then again, I put here delay bounce back, yeah, in between, so that we have an object. And then here we have what ChatGPT generated as some overlay. Unfortunately, for whatever reason, it decided to use the transpose of this. So now X and Y are exchanged, and I was too lazy not to change it back. So because then all these parameters here would be different. Yeah. So let's restart this thing and just run and see. Okay, here we go. Okay, the boundary, I have to admit the boundaries are very ugly. So there is something that I don't remember. But okay, isn't this amazing? One shot, yeah? One shot at it, and we have it. I mean, I'm not saying that we didn't make a mistake. Sometimes we make mistakes, and it still works. That's very dangerous. But you see, you get this. Okay, maybe let me interrupt this. So because of the ugly boundaries, I had to put here a value for the velocity. I make this a little bit smaller, so maybe you see it better. Yes. So this here is the fine grid, and you see this blue line because we have this one line of nodes so this is the outer line of nodes where velocity is 0. This is why you see here a line around it, yeah? And so you can actually observe that this here is a higher resolution, and here you get the coarser resolution just yeah, flows out of this. So this is grid refinement lattice Boltzmann methods. Now, as I told you, with the turbulence, we can make this thing a bit more turbulent by putting here more, putting this closer to 2. So I interrupt this, and maybe I go down so that we see it. And then I run it again. So now we have a little bit more, I mean, also here. So we have a more turbulent behavior that we observe here. Okay, so this looks unphysical. The boundary condition is stupid. What do you think is unphysical?
How can the velocity be increasing over time?
The velocity, in fact, is larger than the input velocity. Yeah, in the vortices, that's not okay. I put here different. Okay, I'll start it over. So the velocity here can be faster. Yeah, that's true. That's so what's so these velocity boundaries, they are ugly, and I don't actually know something. We have observed this in the other example too, and I did not know what happened here. Yeah, so maybe there is a mistake somewhere. Yeah, so but here you now see there are the vortices going off. Maybe I'm putting these, making it a little bit more dynamic. Okay, so initially there are these pressure waves going backward and forward. Yeah, I mean, so we have not taken care of a lot of things that we should have done differently. Yeah, but anyway, yeah. So that's the first time that I try to do a grid refinement in the lecture. So I'm outputting more time steps. So unfortunately, there is I don't know whether I can change here the size of this thing that they have, because it doesn't fit on the screen. No, I don't see how to do it. Okay, it doesn't fit on the screen. So let's focus on the part that we're interested in. Yeah. So unfortunately, so when we have very high Reynolds number and we have these singularities in the corners, we get the spurious vortices down here. To just ignore them for the time being, yeah, and observe just how yeah. So now the way we implemented this, we can use nested refinement several times. I'm not showing this here because then also the procedure that does the display would also have to be nested, otherwise we don't see it. Yeah. So it works. Surprising. Okay, and it's also 6 o'clock. This is how I was planning this. Okay, any questions? Any more on that? I think, yeah, I will stop the recording. Thank you for everybody participating. If you missed the first part of the implementation, then go to the lecture of the previous week. There in the end, we'll have the first part of this.